Hey everybody, I think I'm live, so welcome to the live on Aromatic Chemistry. So I've shared the notes pack with you, it's in the description. I'm sure you've managed to print it off and hopefully we'll be good to go in a second. Looks like there's 6 people on, so that's great. This is a much shorter topic than the rate of reaction topic. I doubt we'll get the whole thing done. Might stop at phenols and sort of make that's like a natural break in the topic, whereby you can sort of stop and pick it up. That's normally what I would do if I was in college. I wouldn't do benzene and phenols all in one lesson. The audio's a bit robotic again. Right, okay. I wonder if it's these headphones, because I'm using the headphones today. Right, okay, tell you what, I'm going to take the headphones out and I'm just going to use the microphone on the actual computer. So the microphone's out now, the headphones are out now, so I'm literally just speaking into the computer. Give it a second to see if it's any better. I normally use a microphone though, because I worry that the sound quality is not great just from the mic in the computer. But I can quite easily run upstairs and get the other microphone. So the audio is fine. Okay, so maybe it was fine for you all the time, Laura, not sure. Just wait for a couple of people to get back and just see if there's a, can you compare with the headphones and now. Sounded better with the headphones in. Okay. Right, let me just run upstairs and get the other microphone I've got. 2 minutes. So I'm back and I've got the other microphones, just like a lapel microphone rather than the headphones microphone. How does that sound? And then we'll start. What time is it? 5 past. Much better. Right. Okay. So, Apple headphones, you are the worst sounding microphone. Now, isn't that something? So I'm running a MacBook with Apple headphones in and the sound quality is terrible. Whereas a cheap microphone from eBay, I think this was 10 quid or something, and you're all saying that's much better, it's even great. Right, okay, cool. Alright then, so top tip guys, if you need a microphone, get a lapel microphone from eBay rather than your Apple one. Sorry Apple, I doubt they'll be sponsoring me now after that. Never mind. Alright then, so aromatic chemistry. Let's get started then. So the first thing I've got there is just some basic definitions, some sort of typical organic definitions that students need, sorry my students, but students need constant reminders of, okay? So I've got the I've got the ones in that are obviously linked to benzene and aromatic compounds. Notice it also says they're arenes. So basically an arene is an aromatic compound. It's just another name for them. Okay. So the definition of an aromatic compound or an arene is a compound, chemical compound, containing one or more benzene ring. So obviously if it contains a benzene ring, we class it as aromatic or arene. Unsaturated, so you'll be familiar with unsaturation with your multiple carbon-carbon bonds, so your alkenes, they're unsaturated. Alkynes with this carbon-carbon triple bond, but also aromatic compounds are classed as unsaturated. Okay, and then a couple of the other ones there, you notice they're in italics, and that's because they're not really linked to aromatic chemistry, but just your aliphatic and your alicyclic. Okay, so aliphatic compounds, compound containing carbon and hydrogen joined together in straight chains, branch chains, or non-aromatic rings. Okay, so in other words, they don't have benzene rings, neither do alicyclic compounds. Okay, because it says there an aliphatic compound arranged in a non-aromatic benzene ring. Okay, hope that made sense. But those first two definitions, these are the ones that are directly linked to aromatic chemistry. Okay, right. So the simplest aromatic hydrocarbon for the case of A level, okay, A level, the only aromaticity that we deal with in A level is benzene. There are other aromatic, you're right, that aren't benzene rings, but for the purpose of A level, we just deal with benzene, okay, in terms of aromatic. Obviously, if you go on to study chemistry at uni, you would come across lots of different types of aromatic compounds that aren't benzene. Okay, it's all to do with, if I remember back to my uni days, it's all to do with the number of pi electrons that are present. It's something to do with the pi electrons. I would need to look that up to say with any confidence, but we are only interested in benzene. Okay, so the simplest aromatic hydrocarbon that we deal with, okay, is benzene itself. And then I always put like the little history side of it, but you don't need to. All right, so you will, if you're going to do MSci in chemistry at an Imperial, you'll learn all about, I'm sure, about aromatic substances. You can come back and give us a little lesson if you want. It was isolated in 1825 from the gas used for streetlights. Found to be colourless, sweet smelling, hence the word aromatic. Highly flammable liquid. Since its discovery, it's been found to be present in crude oil, it's a component of petrol, and it is a classified carcinogen. Okay, so it's a cancer-causing substance. Okay, so as a result, we do not do any experiments involving benzene at college. I think when I did my A-levels back in the 80s, we did some experiments with phenol, which is very similar to benzene, just got an OH group off the ring, and you wouldn't be able to do that now. Okay, it's the health and safety would prevent something like that. Okay, but back in the 80s, pretty much anything went. All right. So the first sort of main section is the structure and bonding in benzene. So scientists, once they discovered this substance, they were very quickly able to establish that its molecular formula was C6H6. Okay, so obviously the race was on to come up with a structure for C6H6. And so after that, using the experimental evidence available at the time, the German chemist, Kekulé, proposed in 1865 his structure for benzene. So that's it there. So this is what we call the Kekulé structure for benzene. Kekulé structure. I suppose, unfortunately for Kekulé, many other chemists weren't convinced by this structure because benzene did not appear to have the expected properties. And for A level, there are three key pieces of evidence which sort of disprove Kekulé's model for benzene. Okay, so often exams have a 6-mark question where students have to sort of talk about the evidence that led the science community to move away from Kekulé's structure and move to an alternative, sort of an updated structure for benzene. Very, very common question, and I've probably done about 3 or 4 videos of exam question walkthroughs where that question's on. So if you wanted to check those out after this, please do so. Okay, so what are the three things? It's lack of reactivity. We'll go into these in more detail on the next page. The length of the carbon-carbon bonds and the enthalpies of hydrogenation, okay, not hydration. Really common mistake I see is students talk about the enthalpy of hydration, okay. The enthalpy of hydration is to do with the enthalpy change when you react something with water. Enthalpy of hydrogenation is about the enthalpy change when you react something with hydrogen. That's what we're talking about in this case. Hydrogenation. Sorry, you can't really read my writing there. The gap's not very wide. It's easier to use the delocalized model, certainly in mechanisms. I'll come on to that, but I typically would use the delocalized model for benzene in the exams, unless I was asked to draw Kekulé's structure. Okay. Right, so let's unpick those 3 bits of evidence now. So if benzene did contain carbon-carbon bonds, which Kekulé's structure suggests, so look, we've got 3 carbon-carbon double bonds in that hexagonal ring. Okay, so Kekulé's structure is saying that benzene has 3 carbon-carbon double bonds. Okay, then if it did have those, then it should be reactive. Okay, just like alkenes are quite reactive substances, so therefore benzene has 3 carbon-carbon double bonds, alkenes have double bonds, should be reactive like the alkenes. And it should be able to decolorize bromine via an electrophilic addition reaction. Under normal conditions, okay? And scientists found out that it was actually quite unreactive, and it only reacted with bromine in the presence of a catalyst. Okay, so benzene is doing something different to what scientists expected from Kekulé's structure. Okay, so that's the first little piece of evidence that's leading scientists to cast doubt over that model. Okay, that Kekulé model for benzene. Okay, it's a lack of reactivity. So that's it, and it's always a good idea to give a concrete example. Okay, so it's lack of reactivity. For example, it only reacts with bromine in the presence of a catalyst. Obviously, if it was reactive, it wouldn't need the catalyst. Okay. Second piece of evidence: if benzene did contain carbon-carbon double bonds, its hexagonal ring structure should be irregular. And that's because carbon-carbon double bonds are slightly shorter than carbon-carbon single bonds. Okay, so benzene should have an irregular hexagonal structure. And in 1829, obviously you don't need to know the dates or anything, but in 1929, sorry, a technique called X-ray diffraction became possible, and it was found that all of the carbon-carbon bonds were the same length. Okay, and they were between the length of the carbon-carbon double and carbon-carbon single. So they've got an intermediate bond length. Okay, so between. So they're all the same length, somewhere between carbon-carbon double and carbon-carbon single. So we would say, therefore, because of that, it has a regular ring structure. A regular ring structure. Okay? And the final piece of evidence you could probably do quite a lot of jobs with a MSci in chemistry. You'd be very desirable, actually. You wouldn't have to stay in the chemistry field. You could go into a lot of stuff. Anyway, I'm digressing. I need to get back to this. Sorry. If benzene did contain 3 alternating carbon-carbon double bonds, as shown by the Kekulé structure, it should therefore have an enthalpy change of hydrogenation 3 times that of cyclohexene. I've got some diagrams to go with this in a second. Okay, so I'll just, before I fill in the last one, so this is cyclohexene. So you can see there, that's the reaction, that is the hydrogenation of cyclohexene. So cyclohexene, when it reacts with hydrogen, it only reacts with 1 mole of hydrogen because there's only 1 carbon-carbon double bond in the molecule, and it produces cyclohexane. And the enthalpy change for that reaction is minus, so it's an exothermic reaction, 120 kilojoules per mole. Okay, so Kekulé's structure for benzene is basically another 2 double bonds. I'll put them in here. So imagine Kekulé's structure is that, isn't it? So that would react with 3 moles of hydrogen, wouldn't it? And again, it would liberate, it would end up making cyclohexane. So you would expect that to be 3 times the value for cyclohexene. Yep, so minus 360. So I'll tell you what we'll do. We will just write that equation underneath. Okay, so that's your cyclohexene. And then underneath, let's do Kekulé's structure for benzene. Okay, so put the double bonds there. That would react with 3 moles of hydrogen, would still make cyclohexane, and the delta H you would expect would be minus 360 kilojoules per mole, so 3 times the cyclohexane value, but the actual value is only minus 208. So it releases less energy per mole than expected. Okay, so it was found to be less exothermic. The enthalpy change of hydrogenation was less exothermic than expected. In fact, 152 kilojoules per mole less energy is produced. Okay, so there's 3 pieces of evidence that sort of cast doubt over Kekulé's structure for benzene. All right, and then we've just got this diagram here where you've got sort of enthalpy change profile almost diagram. So if Kekulé's structure was right, that would put its energy sort of 360 kilojoules per mole higher than the cyclohexane energy enthalpy value. Yep. But because when they measured it, it only releases 208 kilojoules per mole, that means benzene's enthalpy is down here instead. So it's actually more stable than it's expected. So I'll just put there, what is, excuse me, this is telling us that benzene is more stable than expected. and that actually leads to the fact that it's got a low reactivity. Stable molecules don't tend to react particularly easily, okay, because they're quite happy and they don't release a lot of energy when they react. Shouldn't say happy, but you know what I mean, don't you? Right, so this information, so these 3 bits of evidence led scientists to propose an alternative model for benzene, and it's known as the delocalized model. Okay, which actually helps to explain the actual properties that benzene has. Okay, so this here is the delocalized model. This here, okay, delocalized. Structure. But if, you know, in an exam, if you're talking about benzene, you're fine to use the Kekulé structure. And to be honest with you, whenever you go, you know, whenever I have a walk around universities, take students on visits and things like that, 9 times out of 10 on the whiteboards that you're walking around, you would see lots of mechanisms involving aromatic compounds, and universities actually use the Kekulé structure for benzene in all their mechanisms. They would. I'm going to say never. I could be wrong about this, but I've never seen this on a whiteboard in a university. As I've been walking around, it's always been the Kekulé structure. Okay, so but there's nothing wrong with this. Okay, certainly for A level, I would probably, it's easier to use this actually. Okay, and that's basically what I'm saying there. Note that the Kekulé structure remains to be an accepted representation for benzene. Noticed a typo there, sorry about that. And it's still widely used, especially in higher education establishments, which is kind of what that little anecdote I've just told you there backs that up. Okay. Right, so let's move on to the delocalized model. So we're going to look at the bonding in benzene now. Okay, so if you cast your minds back to your alkene, I'm just going to see if red, yeah, I need these are all carbons at these corners. Hopefully you can see them okay. So we're going to talk about the different types of bonding we've got going on in benzene. So I always use these three diagrams to sort of talk about the bonding. Okay, so the first diagram, so this one here, we've got our 6 carbon atoms. Okay, so there they are there. Hopefully you can see that from the red pen. The black doesn't really show. Okay, so what's happening is each carbon atom is using 3 of its 4, remember carbon has 4 available electrons for bonding, so each carbon in the benzene ring is using 3 of the 4 available electrons to form sigma bonds. So those 3 sigma bonds, they're going, so let's pick this carbon here, so that's forming a sigma bond with that carbon. Yep, so that's a sigma bond where you have end-to-end or direct overlap of orbitals. So I'll just put a reminder in the notes there of what sigma bonding is. So sigma bonds, put it up here, direct or end-to-end overlap of orbitals. So each carbon is doing, so that one's going a sigma bond there with that carbon, a sigma bond there with that carbon, and a sigma bond there with that hydrogen. Okay? Right, so let's just make a note of that. So these arrows here, 3 times sigma bonds for each carbon, yeah? Okay, so where's the 4th electron? Well, the fourth electron, each carbon has another electron available for bonding. They are in p orbitals. So let's pick this carbon here. These are all carbons, remember, just not shown on this diagram. So we've lost the sigma framework now. We're just dealing with this fourth electron. So this carbon has its fourth electron in a p orbital. Remember, p orbitals have an upper lobe and a lower lobe. So this electron is just in this region of space, just moving around in this region of space. So is that one, so is that one, and so on. Okay, so each carbon atom has one electron in a p orbital, and they're at right angles to the plane of the sigma bonded carbons and hydrogen atoms. Okay, and so what happens is these p orbitals, they sort of, the regions of space sort of merge into each other. So if I'll tell you what I'll do, and I would normally do this on the board, so here, so let's just imagine this region of space sort of merges into this one. You see what's happening? Hopefully you can. And so the two electrons, these two electrons here, instead of just moving around like that, yeah, and that one like that, they're actually moving around in this region of space here, okay? And if they're below the plane, they're moving around in that region of space there. Now obviously this p orbital can do overlap with this one, that with that one, and so on. So you end up with this region of space here, okay? So the 6 p orbitals overlap sideways above and below the plane of the bonded carbon and hydrogen atoms to form a delocalized, this is the sort of jargon you need, delocalized shouldn't talk and write at the same time, delocalized ring of pi electrons. Okay, so the 6 pi electrons are sort of whizzing around in this region of space here. That's how many have I drawn? 5, 6. Okay, so that's, and they could also be down here as well. Remember, there's only 6 pi electrons, so they're either in this region of space here or this region of space here. Sigma bond is a single bond, yeah. So just quickly go through that again. I'm going to draw another little diagram here to sort of show you the transition of here to here. Okay. So each carbon atom. So remember, there's 6 carbon atoms. Each carbon atom in the benzene ring forms 3 sigma bonds. So 2 with neighbouring carbons. The third one with a hydrogen. Okay, so that accounts for 3 of the 4 bonding electrons. So they're single bonds, yeah. Sigma bonds end to end or direct overlap of the orbitals. So the pair of electrons, so let's say this hydrogen here has an electron. The electron in that orbital there, they're shared. So you get this covalent bond between this carbon and this hydrogen. There's another shared pair of electrons, but they've been shared in such a way that the orbitals have overlapped sort of end to end. So you get a single bond there, sigma bond, and a single bond there, sigma bond, okay? The fourth electron is in a p orbital, so each carbon atom has a p orbital. Remember, there's an upper lobe and lower lobe. So what happens is the p orbital, the region of space that the electron's moving around in, they expand and overlap with a neighbouring p orbital. So obviously I've only shown those 2 there, but obviously that can overlap on that way, and all of them do. So these are the extra diagrams I'm going to draw. So if you imagine So this is the hexagon. So these are the p orbitals. Not the best diagram in the world. So what's happening? This region of space is overlapping with that one with that one, that one with that one, that one with that one, and so on. And then the lower lobes, they overlap, so we get a region, these are starting to merge. Okay, so what does that do? That will generate, so you've still got this sigma framework, where you've got your end-to-end covalent bonds, but you've also got a new region of space above the ring, and you've also got a region of space below the ring like that. Okay, and these 6 electrons can either move around here or here, so in the red or the blue, and this is our delocalized ring of pi electrons. Delocalized ring of pi electrons. Need to look into that, Jake. I don't want to sort of say yes, and I could be, and I might be wrong. So I'm gonna look into that, if that's okay. It's a good question. Don't know the answer to everything. Okay, is that all right for the bonding in benzene? Because we're kind of moving into naming now. But it's a really, really common. Yes, but benzene has a planar. It's a planar, hexagonal, regular hexagonal ring. But it's a really common sort of 6-mark question. Really, really common. And these diagrams here, I would get your head around how to draw these diagrams. Certainly, this diagram here is really useful. This one here, to show the sort of formation of the pi electron cloud. Okay. I'll just show you another diagram. Just remembered a question that was asked a couple of years ago. I think I've probably made a video on this, by the way. But it basically asks students to draw a diagram to show the bonding in Kekulé's structure. Okay, so rather than the delocalized model structure, it actually asks to draw a diagram in Kekulé's structure. So what you would draw is you'd start with that sort of flat hexagon for your sigma system. You'd put your 6 p orbitals into place. Okay, but Kekulé's structure, if I go for red, Kekulé's structure implied that alternating, you had alternating carbon-carbon double bonds. So I'll just put that in there. Okay, you'd have that. So basically these 2 p orbitals would overlap, but that one wouldn't overlap with that one, if that makes sense. So you'd still just have a single bond there, but you'd have like a sort of localized pair of electrons just shared between those 2 atoms there. They wouldn't overlap with each other, but then they do, and so on. So what that gives you would be Kekulé's structure, but drawn like this, it would look like this. So you'd have, this was actually what they wanted in the mark scheme. The diagram looked just like this, believe it or not. You have that, that, and that. Okay, so that's the difference between Kekulé's structure and the delocalized model, because in the delocalized model they all overlap, all of the p orbitals overlap with adjacent p orbitals. Okay, right, I'm going to move off this bit now because I'm getting a couple of comments saying it makes more sense, so that's good. Okay, so a little bit of nomenclature now. So naming organic compounds, aromatic compounds. So In the names, some groups are shown as prefixes to benzene. So these include short alkyl chains, halogens and nitro groups. So I've broken this down into compounds with one substituent group first of all. So some jargon for you, some sort of technical language. Compounds with only one substituent group are called or referred to as mono-substituted. Okay, mono just means one. In aromatic compounds with one substituent group, the benzene ring is often considered to be the parent chain, so the molecule's called something benzene. And then alkyl groups, such as methyl and ethyl, I've got in the brackets there, halogens and nitro compounds, or nitro groups, sorry, are considered to be prefixes. So obviously that goes at the start of the name. So let's draw these three examples, and I'm going to use the delocalized structure for all of this, okay? So propylbenzene is basically a benzene ring, and I'm just going to draw these at the 12 o'clock position. It doesn't matter when it's mono-substituted which carbon you put it on, because they're all equivalent. So a propyl group is C3H7, or you could go CH2, CH2, CH3, if you'd rather see that. CH2, CH2, CH3, okay? Or, if you'd rather, you could have your skeletal formula, so one, so that's your, it would be that, wouldn't it? Almost like a coat hanger. So there's your first carbon, second carbon, third carbon. So that's propylbenzene. Iodobenzene is just benzene with an iodine atom substituted. So it would look like that. Nitrobenzene, which you'll see again in a minute, is okay, NO2. And just, I would always make a point of stressing to my students the importance of connectivity. So the nitrogen is bonded to the carbon on the benzene ring. So make sure they line up. Because if you drew, I'll just show you what's not allowed. So if you drew this, that's wrong. Okay? Because what you're saying by that is that the carbon is bonded to the oxygen. Okay, so I'm going to get rid of that straight away and put it right back to where it should be. So it's the N bonded to the carbon, so it's NO2. Okay, so they're fairly straightforward, aren't they? Next little bit, when a benzene ring is attached to an alkyl chain containing a functional group, so it could be a ketone or an alcohol or something like that, or to an alkyl group with 7 or more carbon atoms. Now I really don't think the exam board are going to be picky on that second point, 7 or more carbon atoms. This is just more for your information. Benzene is considered to be a substituent, and in that case it takes the phenyl prefix. So I'll give you a couple of examples here. Right, so we have got a functional group here, and that's a ketone, isn't it? So because there's a functional group in the substituent, we need to give this a phenyl. The prefix is phenyl, okay? So what is this part of the molecule called? So that's a ketone, isn't it? Because a ketone is literally just carbon, C double bond O, carbon, which is what we've got. Okay, so this ketone part has only got 2 carbons. All right, so this is called ethanone, which is a bit weird. You've probably never seen that before. Ethanone. Yep, and this is a phenyl group because of the way this rule goes. Okay, so this molecule is called phenylethanone. Okay, phenylethanone. So when do you use phenyl and when benzene? So you use phenyl when there's a functional group in the substituent. Okay, so we don't have any functional groups in these substituents, so it's literally just the substituent name as the prefix. So propyl benzene, iodo benzene, nitro benzene. Okay, whereas no, a ketone has a C double bond O with carbons either side of it, which is what we've got here. That is a carbon. It can't be an aldehyde. There's no hydrogen anywhere sort of neck bonded to this. It is a ketone. So I would avoid using the word middle as well. I would just say it's within the carbon chain. Okay, aldehyde has the carbonyl group at the end of the chain. Okay, or the start of the chain, whichever way you count looking at it. Ketone has its carbonyl group within a chain, so that is within a chain. Carbon, carbonyl, carbon, so it's a ketone. Okay, right, next one. So we've got a really long alkyl chain here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can see you've got 7 or more carbons, so we've got to use the phenyl. This is now phenyl because that's got 8 carbons. Okay, therefore phenyl. So I often would sort of say to my students, if that was a hydrogen, yeah, that would just be octane, but it's not a hydrogen, it's a phenyl group. Where is it on the octane chain? It's at carbon number 2. Okay, so this is called 2-phenyl octane. 2-phenyl octane. I know when I always first sort of start aromatic chemistry, the name, I think people think they've got the, well, I'm sure they have got their heads around how to name organic compounds, and then benzene compounds seem to kind of have their own set of rules, which I think unnerves students at first anyway. Hope you don't mind me saying that, but that seems to be what I detect, and I've been doing this for 27 years now, so I've seen it in 20 year after year after year. But it does, if this is the first time you've seen any aromatic stuff, it's obviously going to seem a bit weird. Okay, but it will, you will get used to it, I'm sure. Some exceptions that kind of just have their own, seem to have their own names. So let's just change colour. I'm not keen on the red. Right, so benzoic acid is literally just benzene ring with COOH on. Okay, and again, just watch out for your connectivity. Okay, now I don't want to confuse you, but you could give there is another name for that. You could call it, because that's a functional group. Yeah, so phenyl. Again, using if that was a hydrogen, what would this be? That would just be methanoic acid, wouldn't it? If that was a hydrogen, that's methanoic acid, HCOH. Well, it's not a hydrogen, it's a benzene ring. It's phenyl name, so it's phenyl methanoic acid. You could call that as well. I would call that benzoic acid though. I would call it benzoic acid, okay, not benzene carboxylic acid. But often, there's if you're interested, there's a website called Chem Spider, and it's a database with all the names of organic molecules in, and you'll be amazed just how many names benzoic acid has. So I mean, I wouldn't chance it with an examiner and give a really obscure name for benzoic acid, because the chances are the person marking your work won't know that that's right, and not give you the mark. So I would be really careful with that. So don't try and be too clever. Okay, so just stick to the sort of simple stuff. So benzoic acid. Okay. Phenylamine is a benzene ring with an NH2 group on it, and the nitrogen's bonded to the carbon. Benzaldehyde is a benzene ring with a CHO group on it. That's the functional group of an aldehyde, isn't it? CHO. You could give that a phenyl name. So again, using if that was a hydrogen, that would be methanal HCHO. Well, it's not a hydrogen, it's a benzene ring, so that alternative name would be phenyl methanal. Phenyl methanal. Okay. So now moving on to compounds with more than one substituent group. So some molecules may contain more than one substituent group on the benzene ring. So two substituent groups is what we call a di-substituted molecule. I'm sure that makes sense. You've probably heard it all before anyway. Tri-substituted, tetra-substituted, and so on. Okay. So because we've got more than one thing on the ring now, we need to use numbers in the name to show the relative positions of the groups. Substituent groups are listed alphabetically as per the UPAC naming rules anyway, using smallest numbers possible. So some examples now. So 3-bromo-ethyl benzene. So let's just build this up. So ethyl benzene is that, isn't it? So if that's carbon number 1, that one there, where this is, carbon number 3 is 1, 2, 3, so it's here, isn't it? Or you could go around that way and put it there. Okay, either way, they're both 3. So we'll put it on this side. Okay. 1,2-dimethyl benzene. So that's basically a benzene ring with 2 methyl groups next to each other. So you can put them wherever you want. So if we say I'm going to put the first one there, then the next one you could put it there. That's absolutely fine. They're next to each other, and we're just saying that that's 1 and that's 2, or that's 1 and that's 2. Could have put them there and there, could have put them there and there, there and there, and so on. Okay, so that's fine. 2,4,6-trinitro-methyl-benzene. So let's do the methyl benzene bit first. Okay, that's methyl benzene. So 2,4,6-trinitro. So there's carbon number 2. It's the N bonded to the carbon. There's the 4. And just be careful with the connectivity on this side. It would be drawn like that. There'll be a rule that's, just looking at that question there, there will be a rule whereby alkyl groups are going to take priority over. So you've kind of got it there, haven't you? So the fact that this is classed as ethyl benzene rather than a bromobenzene, yep, is sort of saying that the ethyl has a higher priority in the name than the bromine. So that fixes that at carbon number 1. Okay, so this one here, my interpretation of this name is That's the important bit, the methyl group. Okay, so this is a methyl benzene, which makes that carbon number 2, that carbon number 4, that carbon number 6. Next one, 2,3-dinitro-benzoic acid. So benzoic acid first, COOH, 2,3, so carbon number 2 is that one. So it's dinitro, so it's NO2. NO2. And then the final one, 4-bromo 2-iodo-phenylamine. So we'll start with phenylamine. So that's NH2, isn't it? So 4-bromo, so that's directly opposite is the bromine. And 2-iodo, let's be a bit different and go around that side instead. That's it there. Or you could have put it, obviously, you could have put it there. Right, going to keep going. It's getting close to the end of the hour, but we kind of had a little bit of a delayed start because of microphone issues. So let's keep going and get the reactions of benzene started at least, okay? Alright then, so benzene and its derivatives undergo, I'll highlight the key bits, so obviously it's in bold anyway, so you can see that. They undergo substitution reactions, not addition reactions. Remember, Kekulé's structure suggests addition reactions. They actually found out that they underwent substitution reactions, in which a hydrogen atom on the benzene ring is replaced or substituted by another atom or group of atoms. Benzene typically reacts with electrophiles, electron pair acceptors, so benzene undergoes electrophilic substitution reactions. You'll see more about electrophiles in the mechanism, okay? So the first reaction we'll look at is the nitration of benzene. So notice it's saying here, benzene reacts slowly with concentrated nitric acid to form nitrobenzene. So here's the equation for that. So benzene ring, or you could put C6H6, I like to draw the ring actually, plus HNO3, nitric acid, and that gives nitrobenzene, NO2, sorry my benzene rings are very messy, and water is the other product. So you can see that's a single substitution, so that's called monosubstitution. Okay. The reaction is often catalyzed by concentrated sulfuric acid. You'll see this in the mechanism in a bit. And heated to 50 degrees Celsius. So there's some conditions kicking in now. So this is really slow. So to get it sort of going a bit faster, the reaction is catalyzed by conc sulfuric acid, heated to 50 degrees C. If the temperature rises above 50 degrees C, you start getting further substitution, so you start getting what's called polysubstitution, and that forms the potentially explosive polynitro compounds, e.g. dinitrobenzene. So that's the example we're going to put in the notes. I'm just going to go back to something we've already seen. It's this one here, okay? This molecule here, benzene ring with a methyl group on. Its old name is toluene, okay? So this thing here, if you're interested, is toluene. That's an old name, okay? Toluene. So this here is 2,4,6-trinitrotoluene, okay? So 2,4,6-trinitrotoluene would be this, so NO2, basically what we've already got. So 2,4,6-trinitrotoluene. So that's TNT. So that's all explosive. Okay, that's obviously you've heard. I'm sure you've heard of TNT from cartoons and things like that. So you don't want to be making anything with multiple nitro groups on a benzene ring. It's very, very bad news. Yeah, would be a homogeneous catalyst because the benzene's a liquid, the nitric acid's a liquid, and the concentrated sulfuric acid's also a liquid. So yeah, homogeneous, not heterogeneous. Okay, so an equation for this one. So if you turn the temperature too high, you could start getting something like this. So it would react with two HNO3s, and you'd get two nitro groups on them. I'm just going to put them on the first two carbons, but they could literally go anywhere on the ring. Two H2Os, so you can see it's like double the above equation, and that's called dye substitution. Obviously that's not advised certainly in a college lab, because this thing here is potentially explosive, so we don't want that. Nitrobenzene is an important starting material for the preparation of dyes. I know somebody asked me last lesson, is azo dyes on OCR's syllabus anymore, and the answer is no. But in the old spec you did need to know about nitrobenzene's use in dye manufacture. So sadly that reaction's gone now from the spec. It's used in pharmaceuticals, so paracetamol for example contains a benzene ring, and nitrobenzene is used in the preparation of that. It's also used in manufacture of pesticides, and it's, like I've just mentioned there, it's also used in the manufacture of explosives. Okay, right, so I think we'll do this one mechanism and then I'm going to leave it there. Okay, so the mechanism, we've got basically three steps. The first step is the formation of the electrophile. Remember we said a few minutes ago, benzene reacts in an electrophilic substitution mechanism. Okay, so we've got this electrophile to generate. So here we are here. Oh, actually, what I'll do, I just want to mention this first. So just to reiterate, benzene and nitric acid react very, very slowly without the catalyst. Okay, there's very little attraction between these two species. Okay, and that's partly down to the fact that the electrons are delocalized, so that they don't have a high electron density. They're not concentrated, localized between, say, two carbon atoms, and that means it doesn't polarize the reactant molecule. You'll see that again and again when we do the other mechanisms in another lesson. Okay, so the mechanism for the nitration of benzene. So the formation of the electrophile is step one. So you take your two acids, nitric acid, sulfuric acid. Students often don't think this is part of the mechanism because it's just a standard chemical reaction equation. You get the HSO4 minus ion, you get the NO2 plus ion, and you get an H2O molecule. Okay, so the whole point of that first step is to generate this electrophile. So if I just circle those both in red so they link together. Okay, and that's called the nitronium ion. So I'll give it its name, nitronium. Brilliant. Right, okay, so now we're going to bring in the benzene ring. Okay, so remember what we said a minute ago, there's very little interaction between this and this, yep, because of the delocalized electrons. However, we've now got a positively charged ion, so there is an interaction between these two. Okay, so a pair of pi electrons is attracted to the nitrogen of the nitronium ion. Yes, I'll be continuing with this at 7 o'clock on Wednesday. fingers crossed it goes ahead at 7 o'clock. I had to change it this week. Hopefully that won't happen again. It's your first time here. Oh, well, I hope it's been helpful. And I hope you've understood my northeast accent okay. Yeah, that's coming up at the end, Jake. You've kind of you've beaten me to it because I'm waffling on here. Right, so pair of pi electrons. So it's really important that you take this curly arrow from the delocalized cloud, the circle, not from any of these lines. Okay? So that comes out and it forms a covalent bond with that nitrogen there. So we generate an intermediate. Okay? Right, so where should we put it? Let's put it here. So let's put hydrogen, NO2. Okay? That hydrogen, by the way, is the hydrogen that's already there, but we don't bother showing it in this part of the mechanism, but we're going to show it now. You'll see why in a second. Now, we've got a partial electron cloud now because we've effectively lost an electron from the electron cloud. Okay, so it gets a positive charge, and what I always tell my students is to cover 5 carbons with your horseshoe. Okay, so this partial electron cloud, cover 5 carbons, but it must be open where you're going to put your substitution. Okay, it's got to be open where the substitution's taking place. And on mark schemes, it will tell the examiner to look closely at sort of how many carbons you've covered by your partial electron cloud in the intermediate. Okay, right. Just going to write here that this is unstable. That it's not going to stay like that for very long. So the easiest way for it to stabilize itself is to sacrifice this hydrogen here. So the pair of electrons in this carbon-hydrogen bond are going to be donated. They're going to go back into, and it will reform this pi electron cloud. Okay. So we'll show that with a curly arrow, like that, and that'll generate the product, the NO to the nitro benzene, and this H here, it's got no electrons now because they've literally both, the carbon electron and the hydrogen electron in that bond have gone into here. That comes off as an H+. Okay, and then the final thing, as Jake's already said, we need to show that the sulfuric acid's a catalyst. So in other words, we need to regenerate it. So basically all we do is we take the HSO4- ion, we take this H+ ion, and we reform the H2SO4. So it's the H+ combines with the HSO4-, and it forms the catalyst. So why is the curly arrow going from here? Because this is unstable, because this positive charge. So to stabilize itself, the easiest thing to do is the pair of electrons in this bond leave the bond and go into reform the pi electron cloud. That's why we need that curly arrow there. Okay, that restores the pi electron cloud and generates an H+ ion because this is going to come off. It's got no electrons, so it's an H+ ion. Okay. Right guys, I think that's a good place to stop. Okay, so there's still a few more reactions of benzene to do. So there's the halogenation of benzene, so that we'll look at the bromination of benzene and the mechanism. We need to look at the alkylation, so the reaction of benzene with to get an alkyl group on it. And we'll look at the acylation of benzene to get an acyl group on it. And then we're going to compare the reactivities of benzene and cyclohexene. And then we're going to go into phenol. Okay, and all of that we'll do next Wednesday, 7 p.m. So I'll post a little video probably on Monday of me stood in front of the whiteboard and just explaining what the videos are for this week. Okay, and we need to decide what this is probably going to be the last topic, I'm thinking, because it's the summer holidays. My students break up a week today. Actually, no, they break up. Do they break up today? You do, don't you? I break up next week, but my students break up today. So happy holidays, my students. I know there's a couple of out there. Rebecca, there you go. Happy holidays, Rebecca. Sorry, I'm keeping you working. You're welcome, Laura. You're welcome. What are we doing next Friday? Should we have a party or something? No, I'm only joking. There might be a little bit of aromatic chemistry to finish off, because I thought I would have done more than I have done today. It's take me longer. Maybe I need to stop my little stories. Yeah. The first thing you've watched? Oh, where have you? Can I ask, how did you find out about it, if that's okay? 17th of July? Dear me. 17th of July. Wow. My students did that challenge last week, Jake, and I'm kind of kicking myself that they did it last week. I should have done some benzene stuff with them. So yeah. There was some talk. I know some people put in the chat. Was it last week? Can we do acids and bases? But I went for benzene because I fancy doing some organic chemistry for a change. So 3 more weeks. Dear me. Right. So if I teach after next week, I'm technically on my summer holidays. All right, okay. You chemistry teacher, but you've just started watching now. Well, I hope it wasn't a waste of time. Getting so much homework at the moment. Oh dear. Well, I give my students 1 homework a week, basically series of past exam questions on the topic that we're doing that week. So they've got a rates of reaction homework handing in today, actually, on the last day of term, which I'm going to mark and get back to them. Can I still please do live lessons? Oh, I don't know. Do we not want to have a holiday? We not need a holiday? We'll see. We'll see. Yes, I know you find them useful. I know. And you're putting me on a bit of a guilt trip here. I'm feeling like I can't say no now. Okay, I'll have a think about it. Okay, we'll see. All right then, that's it. See you all on Wednesday. Will I be making any more note videos on the earlier topics? All right, Jake, are you talking about? Let me just try go on, see if this works. If I go into my YouTube channel on the iPad, hopefully the screen will switch. You're welcome, Lucy, no problem. Bye, Laura. You too. Are you talking about, if you're still there, Jake, sorry it's taking ages to load that up. I think, are you talking about these videos here? I'll put the link to the notes on this video for you, Laura. Okay. Okay. I'm still not decided what I'm going to do over the summer. One of the things I've got going in my head is shockingly bad. Okay. There's a lot of topics. That's the only problem in a lot of topics in year 12. Something like 35 topics. Yeah, it's a lot. Basically, need to make YouTube my full-time job. I think that's the only way I'd have time to do everything. To be honest with you, yeah. I mean, I can make some of these videos, these notes videos, but 35 of them, it's going to take a while. The other thing I'm conscious of is the year 13s who are probably going, some of them are going to want to take the exam in October. They're going to need some support. So I might have to switch my attention to those. Haven't decided yet. Okay, I'm rambling on as usual now. So I'm going to leave it there. All right then, cheers. See you later. See you Wednesday. Bye. Bye.